So what I want to indicate is I'm not going to go through everything, but basically it's based on chapter 8 of my book. And there's a outline, meaning table of content. I will follow some part of it and skip some part of it. Meanwhile, it just so happened that this perspective article is about to be published, which is describing a new outlook at the subject of fraction mechanics with regard to polymers. So it's quite very, very fresh in terms of what we need to say. So let's get started. So this is going to be if you like, this is going to be fracture behavior of polymers. So instead of saying fracture mechanics, that's kind of scary, right? You just say fracture of polymers. And we will talk about both plastics and elastomers. Okay. So let's begin with what is fracture mechanics. It become a business when we worry about fracture, of course. But it really is where we need to talk about it when you are given a piece of material and you stretch it and you measure a point where it breaks. It's called sigma B. In our notation, we call this nominal strength, something you can measure. And the fracture mechanics come in only if you suspect that this strength is actually much lower than the inherent fracture strength. In other words, see this projection, I should try to write it smaller. In other words, if that's not the case, let's say if this is comparable to inherent strength, how do we know? We don't know, but let's suppose that's the case. If that's the case, I can convince anyone that the problem of brittle fracture, remember you are very familiar with it, if I draw stress as function of L over L0, engineering stress, it basically breaks there. And we can call that point sigma B. It turns out if you can claim that this sigma B is comparable to the inherent strength, let me for the future just call sigma F to simplify my notation. Then it turns out then you just need to measure, you just need to report when you break it. But that's not the case for a bunch of materials, such as your window glasses. I see the screen is never as big as that big one, so I can write many things on one page. I actually can mention that if you take rudimentary, let's call it window glasses. If you have window glasses, then it turns out this sigma B, let's say it's about 200 megapascals. And based on things I'm going to skip, but it's in chapter 8, people think this kind of atomic solids we can estimate its strength, meaning strength in its idealized structure. And it should be about 1/10 of the Young's modulus, which you can measure. It's very hard. It turns out 1/10 of Young's modulus is already 7 gigapascal. So it's much larger than sigma B. Okay, much larger than sigma B. And we need to come up with a way to explain why they are all different by 2 order magnitude. Okay, this is about 2 order magnitude because this is about 0.2, and this is about 10 or 20. So it's 2 order magnitude. So this is the problem facing people in the beginning of 20th century, long time. How do we explain that? This is much weaker than what. So I warn you right away that you better trust this number that you can theoretically estimate. Otherwise, everything falls apart. Meaning there's no possible if this is not 2 order magnitude apart. Okay, we trust it, and now reviewing history, it turns out it's true that that there is this much discrepancy. So I already skipped a great deal of the chapter 8. So I'm skipping most of section 1 called theoretical strength. I'm picking up only 8.5, the last section, to talk about. And this describes English's paper. English had a paper in 1913 that, in retrospect, it's clearly the foundation of fractal mechanics by any means. It has stronger meanings than we initially realized. So basically it does this. It's a theoretical calculation. It considers a infinite sheet, elastic sheet, and he dig a ellipsoid-like hole. And this hole goes through the entire thickness. And it's an ellipsoid, so we have the longer dimension as 2a, smaller dimension as 2b. And he says the stress at these 2 poles whenever I do this, at these 2 poles, let's call it A, is stronger. So this is a sheet you are stretching like this with the stress of sigma, and it says it's stronger by 1 plus 2a divided by b. And it turns out one way of measuring the curvature of this pole at the pole is to say it is b squared divided by a. So when you do that, it turns out this becomes sigma is still there, 1 plus basically a over a, sorry, I'm touching somewhere, a over rho. Okay, rho is the radius of curvature. So imagine now this hole you artificially calculated is very skinny, very sharp, meaning rho goes to 0. Well, it never goes to 0. Remember, my favorite subject, it's a length. Curvature, radius of curvature is the length. To say length going to 0 is meaningless, so it's always that length compared to what? Well, however you wish to compare. Here you are comparing with A, of course. Compared to A, it's going to 0, or A over rho is infinite, which implies the stress will diverge to infinity. Although this gives us trouble, it does indicate that if you have a hole like this, the stress locally at A, position A, is going to be much larger than the nominal stress. And therefore, potentially might explain why this occurs. In other words, why fracture occurs when the stress is much lower than what you know what the material can bear, can sustain. Well, it would occur if your sample have a flow, as the theoretical result indicates. So this is still very abstract, what I'm telling you. And I'm prepared to actually switch gears. The point is, this result, although very, very attractive upon further analysis, is really giving us trouble because there's no such a thing as stress going to infinity. So how do I think about this? We will come back to this formula much later. Much later. For now, what happens is we are going to switch gears. In other words, we find this is quite difficult to handle, meaning what if your defect is very sharp? We certainly never observed. You see, no material will break without any stress. Okay? And this goes to infinity is the same as saying no matter how small your stress is, your stress at the tip is already very large. So there's a problem. So let me now review for you further about fracture mechanics. I just mentioned fracture mechanics is a business dealing with the effect of flow. Actually, now you can see. It is because you have flows that your nominal stress or nominal strength can be much lower than the intrinsic strength. Now, in order for me to proceed, let me give you a general impression of fracture mechanics. In fact, for whatever we need to discuss for chapter 8, for the perspective article I wrote, mostly we're going to describe so-called linear elastic fracture mechanics. Now, this is not the first time you heard about linear. Well, linear just means input, output are linearly proportional. And elastic, of course, you know what it means. So it turns out that actually fracture mechanics are built on two pillars. In other words, they are just like just like us, we walk on two legs. This fraction mechanic walk on two legs. There are two pillars. What I just mentioned about English, foundationally speaking, we call English solution, that's the foundations for pillar 2. And there is pillar 1. There's pillar 1 due to, my hands can still touch it, due to Griffith. I mentioned about this was 1913. This is 1921. So he actually developed something rigorously based on English solution. So in that sense, English solution is groundbreaking result. So what he did is he says, let me think about this problem differently. Meaning, differently, but nevertheless inspired by English result, which says stress can concentrate. But he want to consider this problem somewhat differently. He's going to consider, since you have a flaw, let me consider introducing a flaw. In fact, in the original problem, of course, he will just look at the English result, which is a flaw like this. I draw a size, but actually this is an infinitely large elastic material. No boundaries on either side. So this is the English result. And today, of course, we say it's actually similar. So it's actually equivalent to this single edge notch. In any case, we are looking at, so in the future, all the subsequent things, I will just do it even simpler. Using this to represent that crack that has a size A, just like this English thing has a size of 2A, half of that, A, it's no longer symmetric, it's semi-infinite, so it's half infinite. But turns out the mathematics and the physics does not change. The point right now I'm trying to do is to describe a bit more about pillar 1, since pillar 2 is getting us nowhere for the moment. And Griffiths considered pillar 2, or established pillar 2. What he had in mind was to think about the following. If this crack is to grow, so let me use this red to indicate that. So if this crack is to grow a little bit, let's call it a delta. I'm going to examine under what condition this is possible that it can grow. So what he had in mind was if you grow a crack, you will have to pay some energy. Meaning, when you form it, this may not be the concept you know too well. When you form a new surface, you need to pay a price. You need to pay energy to form new surface. You all play with soap bubble. The soap bubble can increase its area because you did work and pumped more energy so that the bubble grows. Okay, so that's the concept. Because the bubble grows, you have more surface. So it turns out you have a certain amount of energy you require that's related to the surface tension and the area associated with that crack growth. That's this length delta. I know I already the thickness is T, so there's a T. So that's the how much new area there is. Delta times thickness, yeah? It's reasonable, that's the area that you have. You know. So this is how much energy you have. You are requesting. On the side, you are asking the following. You see, you are basically stretching with sigma of an elastic body. So when you do that, you store elastic energy. Okay? And you can imagine if you have a new crack of this much, you are going to lose some elastic energy that you stored. Right? In the limit, there is no, the whole space is, crack finishes, there will be no storage of any elastic energy. So this elastic energy, if I use a estimate, I think in my book I call it EG, then I can estimate. What happens is it should be involving a volume as I draw that's probably comparable to the size of the cut. So we're going to propose that this this energy is the volume of this what's circled in green, which is a squared times t. And and then there will be a so-called energy density W. So the energy density W is actually something I probably mentioned once before for you. Basically, it's this area under the curve, so-called. And typically, it will be of the value of sigma B. I'm going to ignore B because we're not at the point of breaking. So basically, it's sigma squared divided by modulus. So the slope is modulus. So that's how much area density there will be. It's coming from integrating over this area. So you don't need to go into more details than this. And the change of that, I know I shouldn't write this way, perhaps. The change of that, when you have a little growth of the crack, will be to differentiate A. So you have 2A coming down, and delta A is that delta, and T and W. So if you equate this two, you will find, meaning this is how much, so it's negative actually. Because you have a loss. So if I put a minus sign of that negative, I have a positive. So basically you see it's going to be gamma delta T. On this side, it's going to be on the order of, I'm not going to worry about 2. It's going to be A delta T W. So this is the condition for fracture. Not in another way, in another words, what Griffiths introduced is to consider. I'm trying to accommodate you in terms of notations. If you recall calculus, you realize this notation need to be very careful so you don't mislead yourself. For example, delta usually represent differentiation. So here, so I can let me do it this way. This will allow me to do it right. Yes. It goes. Meaning you cannot see the bottom. It's hard for you to see. Is that right? We can use a little higher now. Probably enough, right? Yeah. Okay. So if I want to get notation right, I can say the area change due to that little crack growth is delta A, which is delta times T. So what Griffiths was trying to do is to ask, if I have a little crack, how much my energy storage will be lost? Okay, and this thing is negative. Such that when I put a negative in front of it, it will be positive. It will be something like 2A delta T W divided by delta T. Which is nothing but basically A W, right? Apart from 2. So this is known in the entire literature of fractal mechanics as energy release rate. Don't be confused about this word rate. It's just for historical reason we call it rate. Rate normally is with respect to time. But here the rate is with respect to changing of surface. How much surface is being added, new surface. But we preserve this word. We call this energy release rate. It is a count of how much energy that will be lost if you have this much crack advanced, delta little bit. Okay? So I want you to remember this is a powerful concept. And I just so quickly showed you where Griffiths has to, build a huge theory to solve this problem. But I just used dimensional analysis, which we use so many times, to get to the same result, that the energy release rate is merely we call it strain energy for elastic material, which I already showed you is nothing but something like sigma squared divided by Young's modulus, which works perfectly in linear elastic material. Because, let me show you the because part. I know for some of you, you want it. For others, you may not care. But basically, because this is essentially a few % of deformation, stress is linear in strain. Strain is nothing but lambda minus 1. So if you know a little calculus, you immediately get this result with a factor of 2 on the bottom, okay, which is trivial. This square is nothing but stress times strain. In fact, if I use 0, I would do that. So it turns out this area, you don't need calculus. The area under the curve is exactly half of that square. In other words, this whole square is nothing but stress times epsilon. But you only have half of it. That's why you have this. And then you can bring in the epsilon back here. Then you get another, right? There is a sigma, and here it's sigma divided by E. So we get sigma squared divided by E. That's the whole square, and you have half of it. Okay. So he is teaching us something. He is saying this energy release rate, if you have a bit of crack growth, I lost a bit of energy stored, and that ratio, that account, is given by the strain energy density times the size of the crack. It's just based on what I dimensionally tried to indicate. And then the fracture criteria that I so quickly, prematurely told you, is merely saying that fracture occurs. Okay, by the way, this number, in honor of this number, fracture energy release rate, in honor of Griffiths in the modern literature, we simply call it G. Fracture occurs when G, you see, I just wrote you G, right? G is basically this quantity times A, yeah? It grows with sigma, okay? This G. Of course, if you load it more, you store more elastic energy. When you lose it, you lose more. So G, now you need to imagine. You have this system here. Your sigma is keep growing. Let me use those terms all the time. You're loading your sample with a crack more and more. G is growing, so-called release rate is growing. And Griffith says, wait a minute, it cannot grow forever. There will be a moment, crack happens. And that moment is when it grows and grows until it becomes gamma. Or since the surface, you create a surface, you create two surfaces, so twice of gamma. Which I prematurely, I told you already in a hurry. If you equate the two, that's this criteria. And of course, we will call this a critical gamma. Critical G, we call it GC, the critical energy release rate. So fracture occurs when G approaches GC, which is given by, if you calculate in detail for that English crack, or the single edge notch crack, it's roughly given by, there's a factor of pi there, but it's roughly given by this, which is equation 8.28a. in book chapter. Of course, I have to complete my symbol. G reaches GC is, of course, when the load is reaching the critical load. So I don't want to forget I have sigma C here now. Okay? And this is a powerful result. Let me explain. This is a result for 30 years I shied away. I never want to know what that is. With a crack of size A, this result says that the break will occur when sigma C squared is GC Young's modulus divided by 2A. Or moving the square to the other side, I have square root. This is the celebrated Griffiths scaling law, if you want to call it. I call it Griffiths scaling law. This is something I shied away for 30-some years. It says the critical load when this fracture happens is inversely proportional to the size of the crack, proportional to the square root of the size of the crack. Okay? Meaning my Kc written as Gc times E is a constant. You see, if you are not careful, you notice I made a dramatic change without telling you. I have now generalized, simply called that the concept of GC exists. It is a constant. In other words, if I complete this expression, if I may allow me to do that. This is the expression, write it down, yeah? Because that's my GC. So if you look at this expression, I played a trick already. If I follow Griffiths, instead of writing GC, I should write 2 gamma. Yeah? I should write 2 gamma instead. And more importantly, indeed, I can convince myself this proportionality constant Kc, in that case, is a constant because it's the surface fracture energy, the so-called surface tension, which is a material parameter, and Young's modulus, which is also a material parameter. In other words, I understand that Kc is a material constant, provided that this holds. And this is, of course, the starting point of Griffiths. So I want you to pause for a moment and think the following. Yeah, quite amusingly, you can think about the following. What are we saying? We are merely saying this, that the critical stress will be inversely proportional to the size of the crack. And for that to be true is the same as saying there is a proportionality constant. In other words, there exists a scenario where if you have a bigger cut, you will simply fracture at a lower stress, exactly described by this form. Okay, that's all, right? So so this is the so-called Griffiths result. So fracture mechanics, the first thing you ever heard about is this law that the critical stress is lower if the crack is bigger. Now, I don't have time to describe the whole paper, but basically, this, okay, let me rephrase it. This is worked out as a theory. For your window glasses, where I start to do this because it will be very profoundly important, where you can compute for what is GC by using what I underlined here, the Griffiths formula. I call it carefully, this is probably, I don't know how often people do that. I call it the operational definition of GC. I will explain eventually what do I mean by operation. So in any case, take a sample, you can make a cut, and you measure the critical stress, you'll get GC. Yeah? And for window glasses, this number indeed is about twice of gamma. Okay? What does that mean? It means, oh, indeed, I understand why Kc is constant, meaning that proportionality constant. Because gamma is constant, because gamma is material constant, so this is why it's true. Yeah? Get it? This much? Yeah? Very simple, right? You already know, many people don't know, or I don't know for 30 years, which is the origin of this expression. Okay, you know now. Now let's fast forward our clock and go beyond window glasses. So you can have a high strength brittle steel. And of course, you can have your dear polymer.
Any notebook here? No.
There.
Sorry, forgot something.
Yeah. And in this case, it could be your polystyrene or your PMMA. Yeah. We covered this for a long time. By the way, just for your sake, that nominal strength of your PMMA or polycarbonate is on the order of 50 megapascals. Here comes the sad news. In fact, this is I still vividly remember about 4 years ago, I lost sleep upon learning this from a master of fracture mechanics. During pandemic, he offered a Zoom class from Harvard. His name is Zhigang Suo. He's very knowledgeable and very active in the area of fracture mechanics. So I was just like you guys sitting in his class, listening to a Zoom class. We knew each other, of course, previously, visited each other before. He offered the following information. Take your brittle steel or your brittle polymer, your dear polymer instead. Oh, by the way, didn't we just say that this story, well, we didn't say it. Elastomers are brittle. I once told you guys, although it's stretchable, but it's brittle because the stress is growing at the moment it fractures. There was no yielding because of TG. There's no yielding to speak. Okay. So for these materials, different type of steels, he offered the following information. It's brittle. You can do take just the brittle materials. Do the same thing. You make a cut, and close your eyes, and see at what point it breaks the sigma c. And you went through the so-called operational expression definition of it. You measure GC, right? According to this here. And he says to my, it's a nightmarish information for me. He says this GC now is much, much larger than gamma. Let's say easily can be 3 order magnitudes larger. What's your reaction upon hearing this? Well, this is why this is why I want to spend a minute to make sure we are on the same page. You have this polymer now, or your steel now. You operationally still could do a measurement, and you find GC. You find this law still holds. This Griffith's law still holds. In other words, Kc is still a constant. As long as I regard generalizing from G approaching gamma to G approaching some unknown GC. Do you follow? There simply magically in this world exists a GC, despite the fact GC is 1,000 times of gamma. You get it? I was in my comfort zone. When GC is gamma, I understand why GC is a constant. Because gamma should be a material constant, independent of the car size. Okay? But why on Earth GC is still constant when it's much larger than gamma? I scratched my head. I did not have an answer. The world moved on because the phenomenon, let me write that down. It's my favorite word. The phenomenology is so convincing and powerful. What do I mean by that? I mean, there exists a GC, despite the fact it's much larger than gamma. You see. And how else we can explain? Well, the GC still carry the same meaning as Griffiths. It's the critical energy release rate that is demanded by the material if you want this material to fracture. We face two problems. So right away, I share the two problems. Now it, of course, all solidified, but at that moment, I lost sleep and don't know the answer. Today, I know the answer, so I can formulate the question without giving you the answer. The question is best formulated, most concise formulated, if it's a pertinent question, and if it is a question that already have an answer. So the question is, of course, why GC is constant. In other words, independent of. So you can independent of cut size. In other words, constant in the sense it's a material parameter. Why? Since it's not related to surface tension anymore. The general view is, because this is true, in addition to creating the surface, you must have lots of energy dissipation. Well, I prefer to, at least without violating anything, I would simply prefer to say lots of energy got released, that's for sure, because that's, I'm not sure I want to call this energy dissipation, because that has a very different meaning. It means that energy was consumed. Whereas here, according to Griffiths, it's about energy being released. So that's question number one. Why this energy release is a constant? And as I mentioned, in the literature, people start to telling themselves, God, since this is true, there must be lots of energy dissipation happening. Unspecified. Second, obviously, what determines its magnitude, meaning the magnitude of GC. This I lost sleep over. In fact, I literally lost sleep for a day or two. I know something is very fishy. So literally, I lost sleep for a day or so. Or woke up early or something like that. Not that I didn't fall asleep. Woke up early. Too excited about what's happening here. Look, I mean, you recognize there was an issue, and certainly bothered by not knowing the answer, okay, in this case. Look how frustrating this is. I just asked you, I just raised that question to you. I said, what determines the magnitude of GC? Okay? Look at this operational definition. Yeah, why do I say here? It's here, right? It's this equation. This equation. Look at this operational definition. Does this operational definition say, explain the magnitude of GC? Does it? Please? I have this expression. Now you can perhaps very soon appreciate why I call it operational. It serves the purpose of giving me a number when I do experiment. But does it tell me why I got that number? Does it? No, it's only yes or no. Huh? Why doesn't? I trapped you, right? Why you? I don't want to, I not only want you to say no, but why it doesn't? Why it doesn't? Yeah, Chase.
Well, A is not always fixed, and then the sigma C is also dependent on A.
You can get that number for sure, right? Because I make us A, I get a C, done. But why is that particular combination? So it turns out that question is, of course, identical to asking why Kc is constant, which is actually more vivid. You see, you have this Griffith's law here already. This is the Griffith's law. But why this particular prefactor? But of course, that's the same question. And I think you guys got it. I really appreciate this. You got it. How I lost sleep. It does not tell me. And magically it works, but it doesn't tell me. Can you believe it? How amazing this problem is? How simple this problem is? It's amazing. Okay. Having said that, let me tell you how much you need to give credit to fraction mechanics. Because they discovered for this brittle, usually linear elastic. So it turns out our polystyrene, our PMMA, our brittle styrene, and highly cross-linked rubbers are clearly all, can be all very nicely described by this level of fraction mechanics. That the GC is constant. You can change your cross-link density, it's still constant. You can do a bunch of variables, swell it, it's still a constant. It may be a different constant, it's a constant, nevertheless. So not only I want to re-emphasize what a triumph, what a accomplishment this was, that G was found to be constant. But actually tell you something I did mention in the perspective article, which is this. This is a bit profound, actually. So watch what I do here. I'm going back to the beginning of whether nominal stress is much smaller than flawless material or not. So I have two expressions, right? Either or, right? This is either or, comparable or not. So I want to tell you, of course, I already mentioned it, but I mention it again. When you have, when fracture mechanics is none of our business. So when we don't need fracture mechanics, when this is the case. because we don't need to blame flaws. What flaw does is it give you an inhomogeneous situation where a flaw is where you have stress concentration. What happens is when you don't have issues with flaws, we call it flaw tolerant. I know, it's just my pen, it's just sometimes very slippery. Flaw. Oops. Tolerant. In this case, when it's flaw tolerant, be my guest. Your nominal strength, sigma b, is all you need to characterize your material. Okay? When you have a flaw intolerant material, such as your window glasses, then a seemingly, why is it seemingly? We call it uncut. A seemingly crackless sample, because it has indeed a flaw that weakens your material, you can no longer use nominal strength to describe your fracture behavior. Both are doing fracture. Both are doing brittle fracture. What I mean by this, let me amplify this in a big time. So on the left, we just need stress to describe your material. On the right, this flaw intolerant material, you have introduced a length scale such as the flaw size, to the point that it is no longer sufficient to use stress to describe your response. So what do you need? Well, pretend this A is nothing but the cut size English and Griffiths considered. I'm just writing the English the Griffiths expression again, except to acknowledge that flaw does what that crack does. So instead of writing that fracture to be happening at sigma C, I better just call that sigma B, shouldn't I? Do you follow, right? Right? That flaw does what these guys consider as a cut size of sigma star, of A star. And now look what you're getting. You're getting the idea that for you to describe the strength of your material, you need not only some kind of stress which still is accessible and observable. Not only you need the stress, you need a quantity that involves a lens. In other words, I know I'm almost mumbling. I'm telling you how to celebrate this fracture mechanics accomplishment. They discovered a quantity, let me formally for the first time call it, this critical energy release rate, saving something, is called toughness. They discovered this quantity called toughness that can describe what's going on. And it's done through Griffith's argument. And it for the first time indicating to you that what you need to describe is no longer the stress, but actually a length. And what is this? It turns out it is what we had called strain energy, or basically it's energy density. So GC, let me write it as bigger. So GC, oops. So GC is a product of some length and energy density. Energy, it's so slippery, the thing is density. Let me try to indicate this to you again. So when you have a card, you have, I'm switching back and forth. Now when you have a card, for example, a crack that you introduce in the lab, or a flaw that embedded inside unintentionally, you will have a length scale. Remember, what I omitted for you, and it's a crime I didn't ask you, is remember whenever we introduce a new physical quantity, we ask what's the dimension. So what's the dimension of this object, GC? By its definition, wow, you had it. Trace all the way back. Look at here. It's energy per unit area. Wow, duh. You are equating that with gamma. It has the same dimension as surface tension, which is energy per unit area. Energy per unit area, watch, is energy per unit area, right? Energy per unit area is the dimension of energy release rate. It is also, let me write it. It is also, let me times length upstairs and length downstairs. Well, it is also energy per unit volume times length. Yeah. And do you recall what is energy per unit volume? A familiar quantity that you use it all the time. Stress. Okay, right? It's stress. So you say, Dr. Wang, can I even do something cheaper? Can I use the scaling argument that you have been teaching us for 10 weeks? Use scaling argument to say my GC should be A times stress, sigma C. Wow, you look at the operational definition, equation 8.28, you find, oops, that's not true. In other words, it changes oops, it changes quadratically with sigma and divided by E. I just tricked you. This sigma quadratic divided by E has the same dimension as stress. And stress has always the unit of energy per unit volume. So too bad the dimensional analysis cannot get you to differentiate this versus this. Stress divided by Young's modulus. Young's modulus has dimension of stress again. So both have the same unit. So you cannot get it. Okay? But we did it cheap enough. We have it. So this is the story. Remember this part because in a way, we'll come back big time on this. And when we try to answer these two questions of why it's constant and what determines magnitude. Any questions? So, yeah. So you can see where is the polymer, right? Of course, where is the polymer in this problem so far? Or where do we cut? I mean, what contributions can we make? Other than asking, right? I think that's the thing that's kind of amusing, right? Asking these two questions has nothing to do with polymer physics. Is that fair? Is that fair? That has nothing to do with fracture mechanics. If you are eager to know what is what is our role of polymer physics, then I can quickly bring you back to that point where you realize you are the master of this subject. It is right here. Or where do I put it? Where do I put it? You can put it anywhere, because I actually mentioned many times. For example, I mentioned it. I have mentioned it here last time. As I said, the story of fracture mechanics is a story of, can I say that? Is a story of this being true. Okay? Because when this is true, there are no flaws in the system. And therefore, there isn't a length scale that I need to consider. So I just have that stress. So how come this is true? Or the question is this true for our polymer? How about that? How about that? Is this true for our polymers? In fact, that part I think we covered, we mentioned a couple of times, but we'll come back to it again. This question of whether this is true, it's kind of in that case, I think it's, I really hope I'm not confusing you in the sense that these two questions, let me maybe bring you back to where it need to be. These two questions themselves have nothing to do with fracture mechanics. Sorry, did I say has nothing to do with polymer physics? I'm sorry. Verbal typos. Right? What I mean here then is something interesting. Then why we bother with these questions? Let's say, let me give you the answer. If this, because that's the way to do the answer best. Let's say I have the conclusion that your polymer belongs to this case, flaw tolerant. I just said you should quit worrying about fracture mechanics. Yeah? If you quit worrying about fracture mechanics, then indeed, don't bother even answer this question. Now, so why people apply fracture mechanics to brittle fracture of polymers and find fracture mechanics to be helpful in describing what's going on? See, this seems to be a little bit of paradoxical because when you have a big crack, you need fracture mechanics. We only said you don't need fracture mechanics when you have this in both sides uncut. And there were no flaws. In that case, you don't need fracture mechanics. Now, switching gears, you don't have flaws, but you do have a big crack. Well, then you say, gee, why you introduce a big cut when you study a polymer? Huh? Huh? It's because we are under the impression that your sample is flaw intolerant, your polymer. In other words, we didn't know this is the answer. Are you with me here? We're going sort of going around like a merry-go-round. I mean, we thought our dear polymer is flaw intolerant. To deal with such a problem, to understand why the strength is what it is, affected by flaws, I simply introduced a cut such that I can operationally arrive at the value of GC. Now you see that? Of course, I still don't know what determines GC, meaning its magnitude, and why GC is constant. If you're all confused, it means it's time you learn. Meaning, confusion is a reminder that something you're not grasping. And that's the best opportunity to learn. But I thought I made it so clear that every part is clear. I'm just joking, but I think this is recorded, so I think you can chew it again and again. You'll find all the logical connections in this. So I think I mixed all kinds of informations, including some that you have yet to appreciate. But that's the story. You have a brittle polymer. We previously thought it was exhibiting a lower strength than what it should be. And we blame the flaws, although we don't specify what would be the size of the flaws, and we proceeded. So that's why we're trapped into the same game of fracture mechanics that every other person dealing with brittle fracture of materials deals with. So I verbalized everything. I know it's being recorded, so at least we're not going to lose it. But basically, there are there is the question of where polymer physics comes in, and as I keep coming back to this again, the physics comes in when we need to determine what is the strength in absence of flaws. Okay, and I further indicated even in a flaw-tolerant material, if you introduce a big cut, then it obeys the English result, the Griffiths result. That big cut will weaken your material. So when we say we have a flaw-tolerant material, what we mean is in your material, the flaws are so small, it does not result in reducing your strength. Meaning, we can regard it as not having any flaw. And it will take some experimental data for you to further appreciate that statement. But I hope you understand that this is ought not to be confused. Just because you don't need fracture mechanics doesn't mean you cannot create a case where you need fracture mechanics, which is to have a big cut. And the reason we previously have so much data on it is because we thought we need that to get GC, because we thought your material has flaws, so I need GC to describe it. Okay? And then, of course, you better specify what is your flaw size. So there are lots of other things I may or may not go through, such as what to do with this problem. I mean, what flaw size you threw in there. In fact, let me just quickly mention the way you do it is you basically yeah, I think that's a little complicated. I'm not going to do it here now. So let's go on. The thing I want to emphasize is Griffiths discovered there's energy release rate. That is a constant for our dear brittle fracture material. It basically says that you have to store enough energy such that when you have a little tendency for the crack to grow, to advance, creating new surface, that will cause an energy release of an amount that appear to be constant independent of the cut size. So that's what it is. So obviously, you can have a size, a cut size this big. You can have a cut size this big. Of course, you have sigma 1 here, and you have sigma 2 here, sigma C2 here. And obviously, sigma C2 will be lower than sigma C1. Things like that, right? It scales as. So, okay, that's it. So now I'm going to, we'll take a break soon, but let me set the stage on the next point. So now we're going to do a little bit of polymers now. It's not like we don't do it. So far, I went through 1.5, that's English result. And then we basically went through 8.2 on pillar 1, and mostly discussed the Griffiths story. So it's 8.8, 2.1. And now we're going to sort of jump a little bit, talk about polymers. This is still under pillar 1 and section 3. And this is a famous story, and it has everything to do with Akron, has everything to do with polymer. So why I say it's has everything to do with Akron is because Akron is famous for doing rubber research, and Thomas is a good friend of Alan Jen, our deceased outstanding faculty member who worked on rubber, including rubber fracture. I tend to think they are no longer with us. I know Thomas definitely was not. Yeah, I don't want to. So in any case, this is work done. You can see if they have to be a very old age at this point. This is the work done in '53. This is supposedly the first study of fracture behavior of polymer. In this particular case, it turns out it's not a polymer. It turns out it's simply vulcanized rubber, actually. And they did something. It's a remarkable paper. I could even upload it to. It's a remarkable paper that got many problems. Meaning, when I say got many problems, we had a fresh, new appreciation and look at it. They introduced a protocol for the next, 70 years now? For the next 71 years, people use it to describe rubber. And I don't know where that, it's really ingenious, the protocol. However, on the other hand, it was motivated by Griffiths' energy release rate, which is an angle of looking at the problem that has given us difficulties in terms of what I just said, why this is so big and why it is constant, right? These are the two questions, remember. We had these questions because we are in this way of describing it, which is energy release rate. So the rest, I want to do it so that you really see a modern view of this 70-year-old problem. But sometimes I think we scientists should all become a journalist. I mean, these guys, when they were alive, we should, just like what happens in biology, we had Bruce Maxwell talking about yield. I didn't know he was talking about yield. I would have visited him. He passed away and said, hey, we have a discussion. The same thing here. I didn't jump into fracture mechanics. And the insight they had is a tremendous one. Probably we'll find somebody who knows the answer. So what they did, very oddly, was to suggest looking at a piece of sample that's very short, very wide. Okay? Very short and very wide. It's a protocol everyone uses. To be proper, to measure GC properly of rubber, you tend to do that. It may waste lots of sample, but inevitably that's what. And yeah, I will not be able to describe fully the story until we talk about the so-called pillar 2. But let me just describe briefly so we can have a break. Indeed, this part of the discussion in the chapter does not go into the depths that we need to talk about in detail. So what happens is, remember, in a single edge cut, remember, in principle, we assume your sample is infinitely large, except having a cut. So A introduced the length scale, which is the cut size. Okay, that much I want to say. That's called single edge notch, SEN. This is called pure shear. What you can imagine, however, is when you have such a setup, very, very short, very, very wide, in theory, it can be as wide as you wish. Then when you draw this way, still always, we will define drawing always vertically. When you draw, you can verify it. We have done an experiment ourselves. For example, you can put some markers on your sample, right? You can make markers on your sample. And you draw. You find, as you draw, the spacing between them do not change. Meaning the width doesn't change. Remember, this is rubber, so the volume is conserved. So all the length change translates to thickness shrinking. Yeah? Get it? No width change. Width does not contract. When you draw, the thickness changes, proportional to how much length you have. Okay, that's one thing. Second, so you can prepare such an uncut sample to do it. And then you introduce a cut. Let's say halfway or significant markup. The most important parameter in the problem is this little height. Let's call it H0. Pretend the width is infinite. Therefore, this cut denoted by red is also infinite. Okay? So the only length scale in the problem is what? Is of course H0. Okay? It's of course H0. And based on this analysis, this clue occurred several times. Based on here, for example, we did it many times. G is a length times energy density. And it's happening everywhere else. G is a length energy density. You can imagine what he derived or showed the G in this scenario to be, or GC, G or GC. It's basically WC times H0. Again, it's the dimension of dimension of stress times length. This energy density has the unit of stress. and this is constant. So we will take a break and leave the subject actually, except to, before doing it, except to tell you if this is constant, it means energy density is 1 over H0. Or how do you think about it? Or let me say this much before we take a break. Or since this is a constant, this product is a constant, imagine when I use a much bigger L0, H0. What does that mean? A much, and then the width is even bigger, so I keep the aspect ratio the same. Okay? Suppose I take, you don't communicate between you guys, somebody choose, he can afford it, he has a machine, he choose this much as sample. Somebody choose a much thinner, much shorter one, which means I'm changing H0. Since the product is constant, it says what? It says when it is much taller, the energy density only need to be much smaller. That makes sense because you have a bigger volume now. Because volume is proportional to H. Okay? So the energy stored in the system at the point of breaking is the same. If it's taller, you have more volume. You only need to store a less density amount of energy. Yeah? So this is a beautiful energy argument, energy release argument. Because it gives me even the insight of how to think about it. A taller sample that has more volume only need to, per unit volume, only need to store less energy because I have bigger volume, such that the total is a constant. That's it. I did not like that interpretation. I did not like that result. We're not going to, even after break, we're not going to talk about it. We'll talk about much later, after pillar 2. That perspective, that perception of what's going on is incorrect. In other words, the origin of this being constant is not because this way I can store the same amount of energy to be released. My God. Then you're really saying this Griffith's approach is not delivering what you think is happening. So let's take a break and then we can resume so that we can. Okay. Any questions? I know you may not have realized this is the way it's going to go, but here comes more of the polymers. So, so just like that problem of different cut. Let's try to reopen it. I think there was an issue of asking me to save. Yeah, okay. Future behavioral polymer. That's a typo. Rewrite. Okay, so we are going to do a little bit of more of a polymer physics side. Before that, I emphasize that with single edge cut, we have Griffiths, something like this. With the pure shear, merely we can simply say that, how do I say it? Perhaps you can say that the WC is given by GC divided by H0. I have not thought deeper on this. But basically, what happens is for different H's, you get different WCs. WC, I didn't emphasize. WC is simply, here's, if you want to know that detail, it's important. So what happens is you take an uncut, you get a stress strain curve. It's always engineering stress. And this side is lambda. So that the W is always just the integration of sigma engineering stress lambda 1 over, from 1 to lambda C. So and this pictorially is just this area. And this boundary of lambda C is defined is the critical strand at fracture. It's always confusing if you don't know it. At fracture of the pre-notched sample. So let me explain. So basically, you have a unnotched sample without this red line. You measure this curve. Let me just you measure this curve, and then you have the cut. You draw it until a critical lambda, which is nothing but L over L0. Apologize. H0 over H, because we use that notation here. So it's the height. So the height originally was H0, and this is H. So you draw. At some point, this notch sample break, and you call that lambda C. And you record that lambda C. And then you go to the uncut and find lambda C, and then you integrate this area. And that's your WC. It turns out this operation involves a rather deep and very clever argument. Basically, these two folks advanced a following idea, very clever. He says, if you crack advanced this much, okay? Let me refer it. Advanced, right? From the beginning to here. So you advance this much. I'm trying to draw a distance. If you advance this much, it is equivalent to somewhere in the interior of the same amount, that part of energy is lost. Very clever argument. The argument was whatever happening at the tip is complicated. Whatever happens at the boundary could be also complicated. But it doesn't matter. If you advance a delta amount here, it amounts to, in the middle of uncut here, this much of stored energy is no longer there. Right? Of course. And how do I calculate that energy? That part of energy is just like that of an uncut. So that's that. Very clever. So everyone use it. Okay, so that's the completely the energy release concept. Let me repeat, right? If I advance this much here, the crack, if pretend crack would move to here, I will exactly lose that much away from the crack in the interior that can be treated as an uncut piece of something. That's the argument. Very, very clever. And therefore, indeed, this energy release rate was found to be constant. But not for the reason that I just explained before we took a break, that this is energy, this much energy released, because it's really not an energy argument, it turns out. So in any case, let's proceed and say a couple words about what we know so well about polymer physics before we move on. And that is the next topic, very famous in the literature, called Lake Thomas. The same Thomas. Lake is another person. They're all friends of Professor Alan Jen. They were model. I will not say too much about anything other than follow the idea that GC is something important to compute. So people start to realize that maybe I can just, at a crack, maybe I can just compute for, right? It's a sample that has a certain thickness. Maybe I can just compute for what is the energy release. Follow exactly the definition of it, right? If you propagate this much, let's say you propagate this much, then the strands here must be all breaking. And let me just calculate it, okay? Go ahead and calculate it. And the thing that's being loudly advertised, remember, at that time, there was already, I think, a disturbance that Reverend Thomas, 1953, he designed this new pure shear method to describe rubber. They already found this is disturbing, much larger than surface action. Okay? So if there's any way I can theorize it, bring me closer to that, it would be great. So this is deeply advertised. So in this, it's a network, so it's nothing really new to you guys. Indeed, the argument was this, that, the energy remember this is energy release rate, so it involves energy per unit area. The energy that's involved is so there are two things that, there is one thing that's right about this, and the rest will have to really, I will have a hard time explaining to you what's going on, because you learned a little bit about Robert rupture without flaws previously. Meaning, what's right about this is he thinks this energy release that give you the quark propagation, of course, involve chain breaking. All right? Moreover, he thinks if the energy to break one bond is this, one bond, then I realize in this chain there are many bonds. So I need to multiply that. In other words, although only one bond break, but each bond stored the same amount of energy, close to that of breaking energy. It's just purely following the energy release idea. The rest is that energy times how many are there per unit area. For psi, cross, I call it x, indicating cross. Each bond will store energy of the so-called bond. In fact, this is the familiar symbol we used before, bond dissociation energy. Each bond does that. And a strand of n such bonds will result in an energy release of n times d. And remember, this is energy per unit area. And therefore, it is the number of strands. Each strand has, let me use capital N, each strand consumes nd amount of energy, and area is A, and that's nothing but the so-called area density that we are familiar with. This area density, in particular, we went through many times, is simply 1 over the packing length times the size of the subject. You go back to information, it's all this. And may I add a little symbol to remind myself, it's not n, but nx, right? Because this strand has a length of nx involving nx repeated units. X just stands for cross-linking. And this size, remember this is so-called end-to-end distance, we call it the size, is of course the square root of nx. And in the strict unit, you may have the characteristic constant and times the bond length. What I'm trying to do, all am I trying to do is to show you that this is proportional to a square root of the strand length, or the number of strands. Number of bonds in that strand. So this is the final important result, that they say you can toughen the material. In other words, your polymer will be tougher. Okay, remember GC is defined as toughness. So a tougher material simply means a larger GC. And this GC is expressed this way, so people would say that your material is tougher if you have a long chain between crosslink, in some sense. Uh, uh, the so I this is the kind of like a probably I could we can save a little time, assign this as homework in the sense you can read that part of the discussion. Basically, you can put in some fairly realistic values for a typical cross-linked sample. So you know Nx. You know the dissociation energy level. You know packing parameter is roughly how much it is. And the rest you know, so you can characteristic ratio is on the order of 5 to 10. And carbon-carbon bond is always 1.54 angstrom, things like that. You end up finding GC, here comes. You end up finding GC roughly on the order, let's say 20 to 30 joules per meter square. And in contrast, I just want to show you. So sometime nowadays, for reasons that is clear immediately, one like to call this, instead of GC, just call it a G0, because it's really the lower bound. Basically, experimentally, GC could be easily more than 10 kilojoules per mole. Three order magnitude higher. So this Lake Thomas model of, you can see, of course, but this Lake Thomas model didn't help us. It didn't, it was not, you have to again interview them, right? They made a model in order to explain that this GC is much larger than gamma, or much larger than whatever. So basically, we find a number that's still very, very small. Since you guys all went through this bond dissociation story, this energy that is used in this argument assumes bond breaks instantly, meaning you exerted the maximum tension on the chain. And that would occur instantly, meaning that would occur on the scale of tenths of a picosecond, 13, 10 to the minus 13 seconds. And of course, our breaking of rubbers never finishes that. It usually occurs on much longer time scales. But that's really not important for this problem. The problem right now is this idealized calculation of GC is still too small compared to experiment. That's a pretty sad story. And in the modern literature, people start to suggest that this calculated GC, people start to call it G0, is simply the lower bound of GC, meaning I'm kind of in a hurry to tell you this part. I don't know when we will come back to talk about it, meaning it turns out in the literature, this is, in that sense, very important. Very sadly, for elastomers, meaning such as our dear rubbers that Goodyear uses in their tires, is not a constant at all. I just said so far, right? You heard the whole thing, that this is a material constant. We even have a question why it is a constant. Okay, not only we worry about magnitude, we worry about why it's a constant. But sadly, and for plastics, for your polystyrene, PMMA, it's roughly a constant. When I say constant, I mean this. It doesn't depend very much on how fast you are stretching until it breaks. Well, for your glassy polymers, it's only a few percent when it breaks. But rubber, as you know, can stretch 100%, 200%, 300%, whatever, right? So for our elastomer, sad story comes, what is the other paper? 1955, I think, is their third paper. That this GC is not a constant at all. A typical way of writing it is something like this. This is known since 1950s, soon after the first paper, 53. The 60s, it start to become very well established. In fact, I may as well, since I have this file here, show you that result, which I cited in this perspective article. Oops, what did we do? Okay, so this is the plot. 1960, for example. So what's plotted is GC. Done in two ways. I showed you only one, the pure shear, and it turns out it's very convenient. I'll go back and forth. It's very, I would have always a hard time drawing it. So if this is the piece you have of your rubber, it turns out you can always take this trouser and tear it, usually supported by a substrate so that it doesn't involve much deformation. So basically, along this line, you can tear it. And you will find you need enough force in order to tear. And T is thickness. If you examine it, you find this has the right dimension, force per unit length. So you can tear. So in general, you can either tear or use pure shear. They give similar results. So in the literature, it's very much often called tear. See, called tear energy. It's the same thing. Basically, toughness. Okay? This toughness is plotted in this three-dimensional plot, so-called, I call it, in terms of, you see, this one is really tear. You see, they use R. The R is centimeter per second. So it's really tear. Okay? So it's not that pure shear thing, which you can do too. It's the same translation. But this one was really tear. So you tear, you find, if you tear fast, oh, you need more force. If you tear at a lower temperature, you need more force. And if you do both, you need even higher force. And it's sort of, I know I use V, so that V is the R in that paper. Sort of in general, V, if you like, is nothing but something like crack propagation speed. Propagation velocity. So you find, if I want to be explicit, it's not just a function of V, but it's also a function of temperature if you are changing, if you are willing to change the temperature. So it's a complicated beast, as that plot showed you. It's not a constant. And people have been in the history try to you do a variety of things. You go to high temperature, you even try to swell the sample so that you reduce so-called energy dissipation. This is a word used because this is high GC is regarded as related to energy dissipation. Basically, you can go to that limit and try to reach a measure of G0. So G0, of course, is nothing but GC in the limit of V goes to 0, by definition. In that limit, F is 0. However, away from that limit, that F can be much larger than 1. So there's this GC. And the current convention is to regard this GC as the so-called fatigue limit. In other words, it's the lowest load you can do that crack still could grow over time in a so-called fatigue experiment. You do many cycles of loading, unloading, loading. So GC not being a constant is very disturbing. Meaning, after all, it's a constant if you don't change the rate. Okay? If you don't change the temperature, it's a constant. When you change geometrical factors, such as you change H, then of course you what earlier fails earlier. But when you change these variables, such as temperature and rate, it's now constant. So one of the, you can see. So one of the very modern concept is, which is written into the perspective article, is actually this point. This is probably a rather important point now, but I guess I should talk about, defer to until we talk about pillar 2. So let's talk about pillar 2. So I'm going to skip some of this situation, in fact, much of this, and jump to pillar 2. So pillar 2 is in section 3. And here you will start to like it in some way, or to see how everything come together. So, as I said, the English solution is pillar 2. It says you have a hole, then the stress is higher. In fact, people separately derive a result for circles. The circles is exactly 3 times, because that's A equals B, right? So it's 2 plus 1. So in a circular hole, you call it, whatever you call it, basically is crack, you have the enhancement of stress by a limited amount, which is kind of interesting. Because it relates to the next point. So this is 1913. After Griffiths, which was 1921, Griffiths was 1921. Things continued. In fact, I failed to indicate to you guys that Reverend Thomas' story in the paper, Pure Shear, they actually, so it's a remarkable paper. Not only did they identify this pure shear as an interesting way to look at toughness, they actually admit explicitly in black and white that I'm not going to bother finding out what happened at the tip. Let me amplify this. In other words, the English result, you see, just says if you sit at that pole, that's the stress. That's the stress. By the time Reverend Thomas did the problem, 1953, it is already known roughly what's happening at the tip beyond English. But this paper says, I'm not going to bother finding out what happened at the tip. It's too hard because what's happening at the tip may be too small to resolve. So it's explicitly in the paper. Okay? So it's an interesting side remark I made. The point I want to make is there is a very celebrated piece of result. 1939, if I'm not mistaken. Surprisingly, I didn't indicate the year on the writing. Basically, 39 or 37. Basically, he had a further description of that help us to appreciate the problem of a crack. So if I could call that tip to be the origin, then this point is R away from that crack tip origin. Now if I ask what is the stress here, they found in the limit of a line crack. In other words, the crack is very sharp. Meaning, in the mathematics, it's just a one line that divides up and bottom and ends at this point. Ends at this point here. green point. And he says, oh, this is a mathematical result. So if you stretch, oops, if you stretch this way, if you stretch this way, which let's call it the y direction. Conventionally, sometimes people like to call this y, and this is x. They say the stress at the red, for example, just the yy component, which is just means it's force locally at this point, is going to diverge. As I approach to r, so it goes as square root of r. So obviously it goes to infinity when r goes to 0. So, but that's away from the tip. Remember, the English result is at the tip. The conclusion is the same. If your crack is infinitely sharp, the stress is going to diverge to infinity. R goes to 0 is the same as the English radius duration goes to 0. I know I so casually called a few times K, KC rather. Let me formally say K is known as so-called stress intensity factor. This is extensively studied by Irving. And it's actually stress in this scenario, square root of pi times A. A is that size. So K often is also regarded as a loading parameter because in the linear fracture, elastic fracture mechanics, K are simply related to G. In this way. I'm trying to figure out which dimension is it. Stress. Basically, I have it here. It's kind of here, so yeah, it's G times. That's what I thought. G times the square of. G is the energy release rate. So this is both good news and bad news. The good news is it tells you if you have a crack, the stress will become, so let's rewrite it. It really says is essentially the same as there are many words for it. This sometimes is known as far field stress or remote stress or remote load. There are many words for it. It all means the same thing. So basically this stress at the tip will be sigma, and then the rest essentially is of the order of cut size divided by R. So when R is much smaller than A, that's how the stress gets intensified. So this is a mathematical result. How much intuition can you derive from it? Well, you derive it by soaking in that this is the behavior of a purely linear elastic material as it approaches the crack tip. Where the crack tip is a line crack, so it's very sharp, infinitely sharp, mathematically thin, infinitely thin. So, so what's the trouble? Everything is fine except when you consider this goes to R equals 0. And what can happen at R equals 0? Well, according to this mathematical result, that stress will be infinite. Well, how can any material you have withstand an infinite amount of stress? Of course not, right? Meaning your material will break down somehow before you approach the maximum. So here's what you tend to draw if you think about your stress as a function of as a function of R, you will have basically divert. I know I draw the not right. So if this is 0, then you really have a sense of this thing diverging. To infinity. Right? Goes to infinity. But of course, no material goes to infinity. Then you ask yourself how much the material can withstand. So this is just one of the sigmas. This could be a sigma 1, smaller than your sigma 2, smaller than your sigma 3. So you could have many curves. I know it didn't draw it well. Basically, you can have many curves. I don't draw it well, but basically it's another line, and you can have another line. So Irving rather, got the idea that this has to be truncated. There got to be a level that this material will give in. And the giving is represented in the concept of yield. Okay? So I try to differentiate from our yield, let's call that a capital Y. So in the fraction mechanics, people, the material must somehow give in. Let's call that level of stress where material give in the sigma capital Y, subscript capital Y. In particular, Irving simply called that you cannot approach further to the tip. You have a region that's limited by the stress. Its stress can only build up this much. And this region, he called the plastic zone. So this zone for sigma 1 is this, for sigma 2 is longer or larger. why I say that is simply because you see, all this thing become the prefactor, right? Sigma times square root of A is this prefactor, and the rest is the 1 over R behavior. And this prefactor, of course, for larger sigma is larger, so push red to the blue line. And the blue line, if I may, the next one is the green line. Right? So that will be the green, the blue, the red, right? So it's like that. That's what prefactor does, right? It pushes this up, right? That's this. So this I do it faithfully because I don't want to miss anything for you. So this is what this is. You got a line like this. And you have the same difficulty as you had before in that, watch the rest of it. You have the same difficulty. For example, your stress is keep increasing, right? As I showed you, this thing is keep increasing. The stress is keep increasing. And just as we are familiar with, until you reach the critical sigma C when fracture occurs. Right? So in that plastic zone, you reach this, sigma reached sigma C, and then the rest is so each of the sides is called sigma P. So at that point, the breaking is sigma P star. And if I flip this equation, you see, basically this size, star means the point of fracture, is basically given by sigma C squared, sigma C divided by capital sigma squared times A. In other words, this plastic zone keeps growing to a value of sigma C at the point of fracture. Just by definition, this is completely, there's nothing, no physics, it's just this mathematical result. And I hated this result too. I says, gee, if the material reached this stress level earlier, earlier at sigma 1, 2, 3, still smaller than sigma C, why didn't break that sigma 1 at sigma 2? Why this zone size has to grow more to some magic number? So it turns out that question is the same difficult question as asking what is sigma C. Well, we just recognize that sigma C is meaningless because that depends on what is the size A. So it goes back to the same question of what determines the magnitude of GC. So it's all related in that sense. And remains the same unhappy person with this pillar too. So equally unhappy, what to do? we're stuck. Don't know what to do. Textbook presents this. I was given this. So there's in pillar 2, there is some further development as a result of that development. The community generally think there's something very complicated at the crack tip. Something very complicated. If it doesn't diverge, it somehow is forming some kind of zone so that the stress cannot further grow. Because stress cannot go to infinity, we know that. But here's one trouble. It's just full of trouble, additional troubles. For example, this is said to be, so now I'm listing it for you, okay? Today, we have this circle as plastic zone, fracture zone, process zone. I ignore, I omit the zone to save some. Damage zone, a cohesive zone, the list go on now. We don't know what zone this is. Something happened. And today, in our work, we found a zone which I will describe in detail next time, stress saturation zone. It's just another name, as if, but there is some substance associated with that. And also, in the spirit, the result is different. So maybe I should show you that to drive home the point. So let me go back to this perspective article in that sense. Where, oops, so the CPU is so slow. Where I can, there's nothing better than draw, carefully draw the figures. So here's this result. Here's this description. I think we should try to observe that, and then we're almost free to go today. On the left is what I just told you. Yeah? What I just told you. Some kind of reaching some kind of level, the material go nuts, meaning we don't know what can happen there, but it certainly cannot accommodate stress to diverge to infinity. We keep increasing stress, blue become green, green become red, almost the opposite of the three colors I mixed up with. But eventually, boom, reach a sigma C, some magic sigma C, magic because we don't know what it is. And the zone grow to a particular size. We call it, RP. P stands for plastic. A star is that critical point. And then things go fracture. ignore all the symbols on the right. Okay, careful, listen. On the right is it for polymers is appeared to be what happened. Do you recognize the difference? In both cases, you claim to define tip stress. The dashed line here, I know it's kind of go crazy on me, and I know I had that experience. If I write something, it will crash. So one side you have the dashed line. On the right side, however, that stress at the tip is linearly proportionally growing as you load more and more, in contrast to locking into a particular value. Additionally, the zone size appear constant rather than growing. The rest of the symbol, as I said, you can ignore it. Other than these two features, away from the tip, of course, the theory is right. That's why we're celebrating it. Theory is right, meaning it's minus 1/2 R in both cases, away from the tip. But at the tip, there's some mystery about what's going on. So coming back to all this zone size, name of zones, what I don't like the most is this one, plastic zone. Because in the case of rubber, what is plastic? The rubber is way above TG. There is nothing plastic about it. Let me rephrase it. I guess we take it so literally, and it comes from our polymer, the name. Although the terminology is pre-polymer. What plastic means? The concept plastic dates before the concept of polymer, okay, by Staudinger. Plastic means irrecoverable. As far as I know, that's what. For your dear, carefully prepared rubber, that can exhibit purely elastic behavior, there's no plasticity to speak about. All the deformation before breaking is reversible. So we already made a terminological difficulty, as if it's terminological, but it's probably conceptual, separately. You guys all just went through brittle ductile transition, the whole 9 yards of it. There is a sense, if you are way below BDT, brittle ductile transition, remember we played that word game, it's incapable of yielding. Because you couldn't bring it to that before the other event occurs. Right? It takes a lot of mobilization, global mobilization of yielding. Again, in that case, what's the concept of plasticity or plastic zone? No, it doesn't exist. So these two things, these two systems from day one bothers me for us to rigidly apply the framework of fractional mechanics to polymers, you see, already, or in addition to whatever other concerns, which is more general, such as GC being much larger than gamma. So what's going on? In other words, when I say what's going on, I mean, well, in fact, I don't need to give you the whole 9 yards, but I can give you 1 yard.
The problem, as often the case in science, is certainly in the familiar polymer physics science that I know of, very often the problem is created by the disconnect between theory and experiment. I'm almost inclined to say that it's so easy for theory to mislead a field. This is not a blame, because it's a very general statement. Here, this Westergaard solution created such a difficulty for us, right? Remember, the remedy, I often just write it as remedy, is Irving's remedy of proposing plastic science, because there's no other way out. What is the reality? Or more simply, to what degree this result holds, meaning, how do I mean? You can rephrase the question. It's a mathematical, beautiful result. It's absolutely cornerstone, in my opinion, in fractional mechanics, because it delivers the essence of how stress builds up toward the tip correctly for linear elastic material. But the question to ask is a trivial one. Your dear polymer, or your dear any system, well, I'm going to touch the question of window glasses. How feasible is it for you to imagine the existence of a crack so sharp it's mathematically zero in thickness, or infinity in sharpness? How plausible it is for a realistic linear elastic material to have such sharp crack forming at the tip. Let me rephrase it. Then you will see this is what a story this is. Let me rephrase it, and you can apply your insight now. I think I probably mentioned already. Your window glasses. Probably one of you have the idea that people use a diamond knife to scratch the window glasses. Boom, it breaks on there. Okay? Or I invite you to go to look at my car. My windshield have crack because of two places I'm repairing. That has a stone hit the windshield of a car, and from it radiating some crack. Some crack, naturally occurring crack. Okay? There are really multiple questions. This is actually is touching the deepest part of fractional mechanics, about which we don't fully understand yet, I don't think, anyway. With that window glass on my windshield, I'm quizzing you. How sharp do you think that tip is? Defined as, I can always remember you have TM, you have even AFM, you can go to atomistic level. If I blow it up, how sharp that is? If I can read, how sharp is it? How sharp is it? How sharp that is, right? I can fit a circle and define a sharpness there. How sharp is it? Window glass. Call that rope. How sharp is that rope? Meaning, I'm asking you to guess. Guess you could get numbers, right? Obviously, this is a length, so you better have units actually. What's the number?
That's pretty good. Maybe like
Window glasses, right? Okay.
maybe like millimeters or how many?
I'm not talking about. So I have a stone that hits my car and radiating some cracks. I'm not talking about the size of the crack. I'm talking about how sharp that tip is, as defined here. He says it's millimeter or microns, whatever, right? Anyone else care to guess? How sharp that is? Through any numbers. So come on, there's no right and wrong. What is that number for window glasses? Silica. Come on, you cannot be clueless. Just any number. Give me another number. Because I didn't like his. So give me one. Of course, that being dimension, being a length, there better be a unit. So depending on what unit I do. How about just this much? Well, the real question, just like the one you heard about GC, what determines, again, it's by its, I mean, rho magnitude. What determines? What determines the magnitude? Fair question. May I venture to say the structure, or whatever you call microstructure. Remember, these are just carbon bonds, and we think it's a gigantic network, polymer, it's an inorganic polymer, three-dimensional. And this occurs, of course, on nanometer scales or angstrom scales. So the question that we have no answer even today is if you translate that same question to a piece of polystyrene, I can put a blade and hammer on it, it will start to crack. And if I don't finish, there will be a crack embedded into the intact part. What is the sharpness of that? Well, according to this, you may say, oh, still it also depends on the structure of your material. What the structure do we have, right? We have a kind of a network that can pull out whatever. And then go to rubber, same thing. What is the sharpness, right? What is the sharpness of this tip? I can tell you something quite intuitive, and I'm certainly very straightforward in that sense.
So that we can get ourselves partially out of this trap. But this trap is there to stay. That is, imagine I do that pure shear experiment with a piece of rubber. Right? This is made a cut. I use a blade, very sharp. And in fact, this is rubber, but this is already kind of, I hope you already see some trouble here. All fracture mechanics test experiments, by definition, let's limit it even to linear, right? Try to measure toughness. And by definition, you measure toughness by introducing a cut. And therefore, you go to the lab. By definition, I don't know, we pray to God or what, pray to whom. You made a cut, and how you connect that with Westergaard solution. That's the question, isn't it? In other words, to what degree this Westergaard solution pertains to anything? So I don't think we have very good answers. We tried, I think, it's disappointing I don't have the answer for you, but there are a few things one can do, and I just don't have the answer for you. So for example, take a piece of your rubber. You go, depending on the case, you can use a scissor. You can use a blade and cut it. Advance the blade and cut it. That action, of course, itself, you may call it, it's a fracture mechanical process. Basically, you advance your blade until it can move and make a cut. And the cut you made, well, let's say you fix a particular speed and particular blade. The cut you made, of course, you have no control of what your rubber is trying to react to it and do what. That, remember, often the trouble with science is theory versus experiment instead of theory and experiment, meaning being one person thinking about both. Why make a cut? What happened to it? What kind of cut did I produce? To what degree the Westergaard solution can guide me? Right? So the ones we haven't done, my student probably should be the one to feel bad about it, is what about for case of rubber? The idea is there. I don't know why we don't have a result. Is I can in principle avoid the cutting, even for plastic too. I can. In fact, we have this in our hands. We just don't know how to have it done. We can have a piece of sheet separating them and then cure, for example. Then the cut is made, meaning the separation is made without any mechanical damage. Do you follow? Right? And all that's left is how thin my film is, which can be less than a micron. We have that in our hands. Maybe some of you guys. So in theory, that result can be compared with the case when you have a blade. That's a difficult question. The easier problem was somewhat of a different one. Is actually something like this. As you stretch your polymer, reasonably cross-linked, it turns out, I think I would, well, certainly let's take a slightly different case where your rubber is highly stretchable. Let's say you can easily draw 3 times before it breaks. In that case, what happens is as long as you cut it sharp, it turns out the material response perhaps does not depend on the nature of that cut, because you will see your tip will blunt visibly. Use a microscope. So for example, I of course exaggerate for you, but of course there are cases like this. But for example, this could be involving a row of 50 microns. How about that?
Wow. You have to appreciate the totality here. We have Griffiths that influence the suggestion of pure shear. Everything is an energy argument. And I even mentioned that Reverend Thomas simply says the tip is too small for me to resolve. So meaning people just gave up on exploring a relationship between what happens at the tip versus toughness. In other words, how far, the real question really, is how far or how much more can we push the pillar two approach? That's the real question. Let me rephrase it. People fall in love with pillar one for 2 reasons. One is it involves energy. It's often sometimes easier to model or understand than stress. Number 2, it's so-called a global approach. It does not care what happened at the tip. It has that operational definition. It just measures GC. God damn, it just measures GC. Who cares what's happening at the tip? Although whatever happened at the tip is reflected in this operational measurement of GC. So, so handy and convenient. If you pursue with the pillar 1, no need to look back at pillar 2. That has this difficulty that I just illustrated to you. Although, on the other hand, you have the opportunity to push this pillar 2 much further by looking at what happened at the tip. Don't assume that nothing can be seen at the tip. In fact, very stretchable elastomers, everyone knows that this thing not only is large, it's completely observable. We call it tip blunting. And once you have a visible tip blunting, then you know Westergaard solution of stress divergence is irrelevant. In fact, the question becomes to what degree the English result, can be invited back to guide us.
to give us insight. So, so I think today I will just end with going back to English result and say a little more. And that would be a good finishing, and because I don't need to diverge into other things when we come back next time. We'll deal with how we come into the field, meaning how in the sense of where polymer physics comes in. So let's talk a little more about English. Can I call that tip? It's just the crack tip. And this is the so-called far field load or remote load. And the rest is something like this. There's a factor of 2. I'm not going to bother writing it down here. And suppose we are dealing with a large crack. Remember we say when polymer, even polymer that may be flaw tolerant, which I will give you a proof next time, you still need fracture mechanics, you still need English result when you have a large crack. So by large crack, I mean A is much larger than rho. So this may as well just be written as sigma A divided by rho. Okay. Let me further write down. Remember Weisengard? That calls K is sigma square root of pi A in a symplectic chart. This is nothing but K divided by square root of rho. Okay? So let me rewrite. Stress at the tip, according to English, is nothing but K divided by square root of rho. Yeah? Remember, K is just this. This is the powerful stuff. So I concluded based on answering the A-B question of how, why is constant and what is magnitude, which I haven't showed you how to do it. But at the end of the day, it turns out much of almost all the insight you need for linear fracture mechanics is the English solution written down right here. What do I mean by all? Meaning it actually is foundational. So the first thing you realize is this, because that's why how I discussed before. Nothing is going to have to form an infinitely sharp crack. I may as well acknowledge the crack is always finite in sharpness, fair? Of a elastic material. As long as it's finite, I can use English. Rho being finite, that's it. Yeah? Rho is finite. Tip does not diverge. Let me see where it carries me. Okay. The burning question about A and B will show up just now. Remember, I was struggling with being told fracture occurs when sigma goes to sigma C, K goes to KC, G goes to GC. And I said, what is that condition of C, critical condition? And watch watch what you do. K goes to Kc is of course equivalent to my sigma goes to sigma C because of the definition. Yeah? So far so good. Yeah? Yeah? On this side, on the left side, on the right side, so far so good. What happened to the right side? What happened to the right side? Right, fracture. So what happened to the right side? I had that insight from immediately from day one, which I had to write it down in italic in the perspective article by saying, let me use, I wouldn't even call the word propose, let me use this fracture criteria. And I blame, meaning I transferred all the credit to Griffiths and Reverend Thomas. Griffiths has a second paper in 1924. So it's in the perspective article that I will be able to release to you guys soon. The paper, this is the same. In there, they both said, man, fracture occurs probably because the stress reaches some value. Oh, Jesus. In fact, just to be precise, I kind of mumbling because let's read together what they said in terms of here we are. Oops. The general condition, 93, line 2170. The general condition for rupture will be the attainment of a specific tensile stress at the edge of one of the cracks. Reverend Thomas, according to one of these criteria, this part is kind of, basically says there could be a stress criteria. That means the cut will spread when the stress at the tip reach a critical value. So it turns out that it's still not exactly what I said, but I credit everything to them. I don't want to be burdened by any of this thing. I just need to be the one to emphasize this thing. So what I'm emphasizing, that I knew from day one, this tip stress reaches inherent stress. Okay? Fracture occurs when the local stress reaches inherent strength. This statement is true whether it is flaw tolerant or intolerant, whether it's window glasses or polymer. You can blame flaws. What the flaw does is also build stress at the flaw tip that reaches the inherent strength of the material. I like this because I don't need to speak about one type of polymer, brittle material versus another. It's all in 1913. It's done deal. If you didn't realize what this little exercise. So basically, I know the answer from other investigations. I traced it all of a sudden. I realized I can trace everything back to this English result a century ago. You didn't realize what I did here. Let me write it down. You didn't realize, I don't believe. I answered the question of two. Remember, in the linear fracture mechanics, linear elastic fracture mechanics, Kc, speaking about Kc is the same as speaking about Gc. Huh? Okay? It turns out you can, I have kind of, yeah, basically, I think if you look at it, the definition, the two are simply related this way in what we have done so far. Okay, so the question, I had question A and B about why Gc is constant, what determines magnitude, is equivalent to the question of why Kc is constant and what determines magnitude of Kc, yeah? And look at what you have. Isn't that what I just did for you guys? By taking you through the steps of going to the critical condition. And look at what this is. Look what this says. Look at what this says. It says Kc is sigma f times the square root of rho. Let me remind you what frustrated me. Kc is also sigma c times square root of A. What happened? Fracture mechanics discovered you need a quantity that involves both stress and the length scale. Operational definition. Whew. That's the stress, that's the length scale. But just, it doesn't tell me anything. Remember we just said. But English told you it tells you everything. In other words, there are two pairs of stress and the length. When you have a crack, you don't have just one length scale introduced. You have two length scales introduced. Got it? You pair one length scale with one stress, you pair another length scale with the other stress, which is inherent strength. Yes. You say, you've got to be kidding me, right? You say. You are laughing at that. That's even better. You got to be kidding me. Why it is a constant or material constant? Because this material has a particular inherent strength. But the big part I was preparing you for is don't tell me yes and no about that tip curvature. Here it comes. Remember, I just quizzed you for rho for your window glasses. It is perhaps 1 nanometer, meaning it is material specific. For window glasses, 1 nanometer. For your dear cross-linked rubber, okay, as I said, it could, where did I say it? It could blunt to 50 microns. And that 50 microns should be your English radius of duration at the tip.
Is this someone you know outside? What's so laughable then? So it's like next time we come back, we're going to talk about sort of the step that led to this point. Because I didn't want to keep you waiting here. The y is constant, the magnitude are both answered. Well, partially. We recognize the physics is all embedded in here. And nobody has a model to predict based on structure. But if rho can change by many order of magnitude between different polymers, different materials, that's an insight about how relevant this parameter is. And that's all in English solution. Okay. Any questions? I think we are done.